Nowadays, mobile phones have become a staple of our society, with everyone from school kids to senior citizens owning at least one. For a long time, battery life is the bane of smartphone owners everywhere, and high power consumption of electronic components in mobile phone is the root of the problem. If you look at the size of first generation of mobile phones, it's beyond the imagination of teenagers. It was really expensive, and the talking time was only 30 minutes. So no doubt, mobile phones have changed the world, and their impact on our society is profound and broad. The ages in which man has lived are named for the materials used, and each of the materials represent high technology of his day. If we assume that the mobile phone, the advancement of mobile phones at a fast pace, and a natural question is, what is the future mobile device technology? The future mobile phone will definitely be thin, light, smart, fast, and flexible. The question is, what kind of electronic materials can meet these constraints? The basic function units of the hardware for digital information are transistors, which have been evolving from a vacuum tube to an integrated circuit. Now, scientists have demonstrated atomically thin transistors with high efficiency and low power dissipation. Here is an example of atomically thin materials called graphene, which can be easily exfoliated from graphite using Scotch tapes. And the transistors made from graphene show interesting properties and sometimes extraordinary electronic properties. For example, the graphene quantum dots transistors can process digital signals through the gate voltage at very high speed. Its dimension is so small, and the power dissipation is extremely low. Importantly, it's transparent and flexible. So electrons in graphene can move very fast. If you assume the speed of electrons in silicon transistors is equal to the speed of a person walking, then the electrons in graphene fly like missiles. Electrons in graphene show quantum phenomena. And this creates new concepts of electronic device. For example, for photo detection, for energy harvesting and storage. The qubits in the graphene nanoribbon controlled by the gate voltage underneath are ideal for quantum computation. The power consumption of electronic components can be largely reduced if superconductor wire are used. This is the world's smallest carbon nanotube we discovered in our lab at HKUST. They are superconductor, and the size of 1 million of such carbon nanotubes is equivalent to that of one human hair. So the size of transistor in modern CPU is already in the dozens of nanometers. The number of transistors in CPU such a small platform has increased from 2,000 about 40 years ago to 1.3 million nowadays. Further increasing the number of transistors is a big challenge to scientists. The current largest R&D project supported by European Commission is called Graphene Flagships, targeting on application of graphene and other 2D related materials. The present engineered materials and technologies are insufficient for future development. Smart materials, matter materials with designed properties and atomically thin 2D crystals are all tomorrow's engineered materials. Most objects in our daily life are not planar, but bendable or foldable, like documents or textile. So the super flexible electronic devices are amazing and will revolutionize the lives of coming generations. So we believe the 2D materials we're currently studying will have a great potential for technological applications, not only in flexible electronic devices, but also in biological, chemical detections, energy storage, like solar cells and batteries, and etc. So this ends my talk, and thank you very much for your attention. Thank you.